Okay, this is part 2 of the lecture on the problem of induction, and in this part we're going to look at some potential solutions to the problem of induction. Some modest solutions, you could say. So let's just get started. A quote from C.D. Broad, a famous intellectual who was alive through most of the 20th century. And C.D. Broad said that induction is the triumph of science and the disgrace of philosophy. And he was a scientist. So, I mean, this is a pretty good slam on philosophy. Perhaps scientists, who cares about the philosophical problem of induction? Because science has used induction for a long time and has been quite successful. So, yes, so much for philosophy. Interesting thing, though, C.D. Broad was actually a philosopher. He wasn't a scientist. So it's someone from the camp of philosophy themselves who's saying that, hey, this issue that philosophers have drawn attention to, hasn't really impacted science that much. And I think Broad is right. So explain why. Here's some basic facts. Fact 1, scientists have used inductive reasoning for centuries. Okay. Fact 2, science has progressed a lot since the scientific revolution. Here's a picture of Galileo looking through a telescope when he first discovered Jupiter's moons. And since then, we've been able to develop vaccines, map the human genome, explore outer space, laser technology, and I could name a bazillion more scientific accomplishments, as could you. So here's the deal, though. You don't get fact 2 without fact 1. That is, you can't really explain science's progress without, taking into consideration the fact that scientists have used inductive reasoning. Some other considerations. So statisticians and scientists who rely heavily on statistics, such as epidemiologists, they are aware of the limitations of perhaps particular inductive inferences that they make, particular inductions. So, for example, that's why statisticians will report on confidence intervals and margins of error for particular inductive statistical inferences they make. So not all of you have taken Stat 250. I'm sure quite a few of you have, so you learn about this stuff, but those are just terms to explain how much confidence you should put in a statistical inference and what's the likelihood of error. And there's formulas to calculate that, which I will not bore you with in this lecture. If you want to learn more about it, take Stat 250. But many of you, when you were taking Honors 110, you probably came across those terms. In the realm of science right now, it's relevant to things like epidemiology when we're calculating COVID-19 fatality rates and hospitalization rates based on limited amounts of data. Anyways, to be that as may, though, scientists are aware of the limitations of particular inductions, and they often are transparent about the limitations of particular inductive inferences that they make, especially in statistics. These limitations, though, they are specific to those particular inductive inferences, rather than all inductive inferences. So an confidence interval or margin of error, when you're doing some polling, that's going to be, that particular margin of error will be a limitation specific to that particular statistical study, that particular statistical claim or conclusion, rather than, all statistical studies. Just keep in mind then, the limitations are specific to particular inferences, rather than all inductive inferences. Here's another consideration. Most human beings can recognize better and worse inductive inferences. Here's an example. Suppose you wanted to find out the general attitudes of voters in Northern Virginia towards a politician. So perhaps the politician hired you to do some polling. Should you only poll the wealthy bankers playing golf at the McLean Country Club? No. In fact, I think most 12-year-olds know that. Maybe most 10-year-olds could figure this out. I've taught philosophy to 5th graders before, and I think they could recognize what's problematic with this. Why? Well, it's the local fact that the voting population of Northern Virginia is far more diverse than just the elite bankers golfing at the McLean Country Club. You have people of different careers. They live in different locations. They have different income levels than bankers. They have different levels of education than bankers. And they're probably going to have different attitudes towards a politician than the bankers, okay? So again, most people can recognize better and worse inductions. And the fact is, there are better and worse inductions, okay? Some inductions are better than others. And again, statistics textbooks provide many techniques on how to improve inductions. Again, this is stuff you probably remember from Honors 110. Get a bigger sample. Get a randomized sample. Get a more representative sample. Avoid various selection biases, okay? So we have techniques to improve inductions, which means that there is better and worse inductions, okay? Here's the problem, though. There is still this problem of induction. So how do you reconcile, A, the fact that there are better and worse inductions that you can recognize? I mean, some objections are just objectively better than others. B, science has progressed because of science's reliance on deductive reasoning. Science's reliance on induction explains the progress of science. You would not have all these innovations today if it wasn't for the fact that scientists use that type of reasoning. But still, there's C, that's Hume's problem of induction. If Hume is right, inductive reasoning is circular. It begs the question. Scientists have these beliefs they have because of mere psychological projection. And perhaps the progress of science has just been due to sheer luck rather than a certain type of reasoning, okay? So it's still worth exploring why, how you can reconcile these three facts, A, B, and then Hume's alleged problem of induction. And it's worth exploring. So what we're going to look at today is what's called a local material account of induction. Now let's just get started. So Hume's problem of induction shows that there is no one universal inductive schema that justifies all induction. So there is no one universal inductive schema that justifies all inductions. So this argument is a non sequitur, which is Latin for it does not follow. It's a fallacious argument. Premise 1, there is no one universal inductive schema that justifies all inductions. Therefore, no particular inductive inferences are justified. Okay? This is a non sequitur. It is possible that 2 is false, even if 1 is true. Even if there is no one universal inductive schema that justifies all inductions, it does not follow that no particular inductive inferences are rationally justified. 1 can be true and 2 can be false. Every inductive inference also requires additional assumptions in addition to the observations used to support the inference. No dispute there. It does not follow, however, that there is just one additional assumption that every inductive inference requires, such as Hume's uniformity principle. So it doesn't follow that every inductive assumption requires this, assumption that the future resembles the past or whatever. So again, this is another non sequitur or a fallacious argument. Premise 1. Every inductive inference requires additional assumptions in addition to the observations made to support the inference. Therefore, there is just one additional assumption that all inductive inferences require. Again, 1 can be true even while 2 is false. Okay? 1 can be true while 2 is false. It's false that there's just one assumption that all inductive inferences require, such as, Hume's uniformity principle. So according to Hume, the additional assumption that all inductive inferences rely on is again the uniformity principle that the future must resemble the past. There's problems with that principle in general. For one thing, we don't always assume that the future resembles the past. For example, if I flip a coin 3 times and it lands heads, I'm not going to assume that we'll always land heads. So humans don't have this thing explaining all of our inferences, okay? And another point is, instead, different inductive inferences rely on different assumptions, okay? And these different assumptions, they're usually facts about the world or well-supported theories, okay? So for example, scientists don't explain the fact that the sun will rise tomorrow from Hume's uniformity principle. Instead, scientists will point to other facts about orbital mechanics or our theory of planetary motion, okay? That's how they explain the fact that the sun will rise tomorrow. Let's take a look at 2 inferences. 2 chemistry inferences. Inference 1. Some samples of the element bismuth melt at 271 JC. Conclusion, so all samples of the element bismuth will melt at that temperature. Inference 2. Some samples of wax melt at 91 JC, so all samples of wax melt at 91 JC. So inference 1 is actually a very secure inference, and if you read a chemistry textbook, you'll find it in there. Okay, bismuth is an element, and so if one sample melts at a temperature, since all other samples are the same element, bismuth, they will also melt at that temperature. Inference 2, though, is insecure. Here's why. Wax is a generic name for a bunch of different types of substances, and they all have different melting points. But bismuth is the name for one substance, one element. So what makes inference 1 better than inference 2 then is not the structure, the formal structure, the schema the argument uses. Instead, it's a particular fact about bismuth and wax. Bismuth is an element, whereas wax is a name for a bunch of different distinct substances. The only thing they have in common is that they are hydrocarbons. So again, what makes inference 1 good, inference 2 bad, is particular scientific facts about the natures of bismuth and wax, respectively. It's not some universal assumption that's troubling, like the principle of uniformity, and it's not the structure of the argument. It's particular facts. So, inductions then are not successful because of their formal structure, or because they rely on some universal assumption that is supposed to support all inductive inferences, like Hume's uniformity principle. Instead, most successful inductions are successful because they rely on assumptions that are particular matters of fact. So let's go back to our first example from voter attitudes towards a particular politician. The reason you should not only poll the wealthy bankers playing golf at the McLean Country Club to find out the general attitude Northern Virginia voter attitudes have is because of the local fact that Northern Virginia is comprised of many people in other demographics. So the McLean sample is not representative. This is a local fact about Northern Virginia's demographics, okay? Northern Virginia isn't just a bunch of wealthy bankers in McLean who play golf at a country club. And that's a local fact. That's a local fact that's well established. And then that explains why this particular inference would be a bad inference. It'd be an unreliable inference. Okay? It's not the formal structure of the inference. It's a fact. It's a particular fact about a very specific geographical region. So if you're going to critique a particular inductive inference, then you shouldn't critique it using Hume's problem of induction. That's just weak sauce, all right? So if you're going to criticize like COVID-19 fatality rates or the effectiveness of mask use, don't use Hume's problem of induction. That's just not going to be very effective. And again, I'm not saying that you should criticize those. I think if you read most of the peer-reviewed articles, they're pretty well-supported inductions themselves on the COVID-19 fatality rates and mask use and stuff. But if you're going to critique a particular induction, for any scientific induction, you're going to pay attention to the particular features of the induction and the particular facts used to support the induction, which you already know how to do. Okay? And that's the strong sauce. That's how you criticize a scientific inference. Okay? And like I said, you already learned how to do this in Honors 110 when you're doing those awful engaging sources activities. For many, many weeks in a row, you're just spending all this time in one peer-reviewed article, and you would have that section where you have to think about the limitations of a paper. Well, many of you were writing about the limitations of particular inductive inferences, and the weaknesses you draw attention to would be due to particular facts about the topic at hand. Okay, so many of you are already very skilled at this. If you want to geek out and read more about this stuff, check out John Norton's article, A Material Theory of Induction, and Samir Okasha's article, Does Hume's Argument Against Induction Rest on a Quantifier Shift Fallacy? This is where I pulled a lot of this lecture from, those two articles. They're fairly technical, so obviously I'm not going to require them, but if you want to nerd out, I'll post them on Blackboard. Some of you might want to read it. The end.